Hello and welcome back to another lecture from Organic Chemistry. Last lecture, we were talking about IR spectrum, and we said that whenever you see a spectrum, put a line somewhere around 1500, and the region that is 1500, less than 1500, we called it fingerprint region, and we said it's not really that helpful. Why? Because it's going to be so crowded. So crowded. The one that we were going to focus on it will be the region is higher than 1600. Between 16 to 1900, you will have double bond and triple bond. There are 21 to 2300, and something higher than 2900, you will be dealing with H that attached to carbon, nitrogen, or oxygen, and those they will actually give you idea about what you're dealing with. Okay. And the area that is higher than 1500, we call it the diagnostic region. So your zoom or focus is going to be on a region higher than 1500. Okay. The spectrums that here, I see two spectrum here. One it says for 2 the propanol, and next one is for 2 butanol. Okay, clearly one it has 4 carbon. This one it has 3 carbons. Okay, as you looked, like the spectrum, they look like the same. Okay, and so for now, I can say you have CH. Okay, CH here, and also this region is showing me that I have OH. I can see the same thing here. So I can't really differentiate those two spectrum from each other. Why? Because you're looking for functional group. And what do we have, common between those two molecules? OH. Okay, so the functional group in both cases is going to be the same, and that's not going to be surprising to see the same spectrum for both of them. Okay, now if you see, like if you start getting different electronegativity, because you have different electronegativity, you will have different polarity, and that difference in electronegativity, it can be achieved through different in hybridization. Okay, different in hybridization. As you increase the percentage of s orbital, because it gets more electronegative, so 50% S and 50% P. As you increase the S character, because it gets more electronegative, you will be dealing with a shorter bond. And because it's a shorter bond, you have to spend higher energy to vibrate it. So CH, when it's attached to sp3, okay, and the carbon with the sp3 hybridization, you need to spend 2900. If you turn it to CH, like to sp2, now that percentage of S from 25% went to 30, almost 33% S character, the bond got shorter, and now you have to spend higher energy. And if you push it to 50%, you need to spend 3300 to vibrate that bond. Okay. So as you see, okay, for alkane, because we have sp3 carbons, all the carbon are saturated and they have sp3 hybridization, the CH stretch is going to show up around 2900. Okay, so around 2900. For alkene, you have sp2 hybridization, so you will have a carbon that's attached to another carbon, and that carbon might have hydrogen, okay, hydrogen attached to it. This carbon is sp2 hybridization, and because it's sp2 hybridization, the bond is going to be shorter. And now that it's shorter, it will cost you more energy, and the energy is going to be around, say, 3100. And if it's alkene, that's going to be sp. Okay, you have 50% S character. You need to spend way more energy to vibrate, okay, to vibrate or stretch actually that bond. And in this case, it's showing up around 3200. So as we move from sp3 to sp hybridization or an increasing S character, the bond gets shorter. Because the bond gets shorter, you need to spend higher energy to vibrate it. So the wave number is going to go to higher wave numbers. Okay. Now, what will happen if I put, methyl groups, for example, methyl or carbon or another add anything other than hydrogen around the double bond? So instead of saying, for example, this triple bond, instead of saying CH on both sides or one side, you replace them by, let's say, bromine. And this side, you can put bromine or chlorine. It doesn't matter. and you have a triple bond. Because I don't have an H in H attached to carbon anymore, I'm not going to see a peak around 3,300. And this is going to be the same story when you are dealing with double bond. So the R is the alkyl group, and alkyl is not equal to hydrogen. That means you're not going to see, you're not going to see a peak around 32, 31, or 3,200 whenever you have alkyl group instead of hydrogen. Okay, let's practice some example. Okay, okay, we have 3 compounds. Those are our compounds. Give me. Those are our compounds. And we need to assign them to the 3 spectrum that we are dealing with. Okay. And I'm going to highlight this region, and then let's see what's that region. That region represents CH. Okay. And in this case, you have a carbon with sp3 hybridization. Okay. And where's the 1500? This is going to be the 1500. Okay. So let's highlight the 1500 is somewhere there. So let's say this is the 1500. I don't see, specific peak higher than 1500. Okay, so I'm not going to bother much about this region. I can ignore it for a second. The main character here, I have a 1 peak around 2900 or 32, 31, 30 maybe. Okay, next, let's find the 1500. The 1500 is somewhere here. Okay, now we have a new peak. And what's peak? That's a new peak. Okay, also, we got something here. We got something here. Okay. So we do have this. Okay, we have that one. We have it in all of them. So that's common. And that represents CH. And carbon is sp3. Okay. But we are getting new peaks. We're getting new peak, and that peak is right, okay, here. If I find the 1500, that's going to be the 1500 is somewhere here. Okay. This peak showed up somewhere there, and now is shifting here. Okay, let me highlight that peak. So now the peak shift there. Also, I got a peak here. Okay, that peak again is shifting to higher wave numbers. Okay. So the top one, it has only carbons with sp3 hybridization between all those compounds, those 3 compounds. My guess is going to be this. Okay, this is going to be the first compound. Okay, so the first spectrum belongs to that compound. Okay, and now I have 2 spectrum, number 2 and 3. They looks the same. Only difference between them position. Okay, position of the new peaks we got. Okay, we have a peak that is between 16 to 1800, between 16 to 1800. That's going to be double bond of carbon-carbon. So that represents a double bond of carbon-carbon. And I got a peak that is around 21 to, let's say, 2200, and that's going to be triple bond between carbon-carbon. Okay, and how about the peaks? Okay, the new peak that we get after 29. Okay, look, we have the same peak here. So that cannot, okay, that cannot be another CH, with the sp3 hybridization. That peak is a CH, but carbon, it has sp2 hybridization. So that carbon is attached to another species, another carbon or another atom through double bond. Okay, but that carbon, it has sp2 hybridization. Okay, and again, I see a shift, and this one now is showing up around 32 or between 32 to 3400. So I'm going to say this one is talking about an H attached to carbon, and the carbon is involved in a triple bond. So this carbon, it has sp hybridization. Okay, S character here is 50%. S character, this one is 33.3% S character, and the top one is only 25% S character. As you increase S character, the bond length gets shorter, and it will require higher energy to vibrate it. Okay, so I'm going to assign this one to the second peak, the second spectrum, and that's is going to be the third one. Okay, another example. Okay, here you can see more actual detail about about the peaks that we assigned. Okay, and I'm going to leave this one. I'm leave it to you to go through them and carefully read the notes here. Okay, we have two compounds. Okay, both compounds, they have triple bonds. So let's highlight the triple bonds. Okay, and one of them, it has carbon with a CH bond. Okay, so it has a carbon. So it has a carbon that is H attached to it. Okay, so that means around 3400, I should see a peak. I should see a CH peak. And here you go. I see a peak here around, higher than 3000, or maybe if this one is 3500. So that peak is around, as it says, it's 3300. And that should be an H attached to a carbon, and that carbon is involved in a triple bond. Okay. So we have a carbon involved in a triple bond and an H there. The frequency, or the way the peak that we see there is for CH vibration. Okay. And I don't see any peak here. Okay. I don't see any peak higher than this one. Okay. And that one. Okay. And maybe okay, let me use yellow for this region. That's represent CH with sp3 hybridization. Okay, and that's gonna be this peak. Okay, I don't see any peak here. It means I don't have H attached to carbon with the sp hybridization. And if you zoom on this region, okay, you see carbon is not connected to hydrogen. It has two carbons on both sides. Okay, so you're not gonna see this peak. Okay, that peak, you're not gonna see it. Okay, but you should see like a carbon-carbon stretch. And I'm talking about triple bond, okay? And yes, I see it, okay? I see that stretch, and okay, the stretch is here, okay? And that stretch represent, the triple bond, okay, triple carbon-carbon bond. So how do actually I connect those two compounds to the two spectrum? The top one, because it has a stretch around the 3300, okay, it's gonna be this molecule. Okay, and number two, it will be